Okay, so hi everyone again. Hope you're surviving the apocalypse if you're in the Bay Area, and hope the apocalypse hasn't quite reached you if you're elsewhere. So, as usual, let's briefly talk about what we discussed last time. So last time there was really just one big thing which we covered, which was Belt inequality, or more specifically the CHSH inequality. We phrase that in the form of win probabilities for the CHSH game. You can also just write it as some specific inequalities between correlation functions. But really the sort of key point is that no local hidden variable model can simultaneously explain all the correlations, measurements, and entanglement states. So if you know in advance what the measurements are going to be, then you can choose your hidden variables in order to explain the correlations in those particular measurements. But there's no way, as long as the people doing the measurements are free to choose the measurements that they like, what basis they want to measure, then there is no way to explain the results with a classical real theory that is also local and doesn't have information traveling faster than the speed of light. Great. So today, we're going to talk a little bit more about Bell states. In particular, we're going to talk about how they can be used to do QKD. So we've already seen one way to do QKD. We're going to see another way. And then we're going to move on to really starting for the first time to talk about quantum computers. In particular, we're going to sort of briefly introduce the circuit model of quantum computers and some important unitary gates. Actually, probably the most important thing we're going to cover in this lecture is just going to be some notation, but it's very, very powerful notation, which is called circuit diagrams. In other contexts, it's also known, so it's basically the same thing as what's called tensor networks. Originally, it was called, I think, Penrose graphical notation, but it's a very powerful way of just writing down the algorithms used by quantum computers, and it's really the way we're going to do throughout this class. Okay, but before we get to that, we're going to start with QKD. So previously, we talked about BB84, which was named after Bennett and Brassard. It was invented in 1984. Now we're going to talk about Ekert 91, which unsurprisingly was invented by Arthur Ekert in 1991. We're not going to talk too much about this because it's really essentially the same protocol as BB84, but it's sort of a nice way to think about it that makes explicit. It's sort of easier to see why it's impossible to break. Okay, so what happens in BB84? So in Ekert 91, Alice and Bob somehow set things up so that they share a Bell pair, phi plus 0 plus 1, 1. How might they do that? Well, a very simple way, which is basically the same thing as BB84 in the end, is that Alice can make a bell pair in her lab, and then she can send one of the qubits to Bob, right? But we're not going to worry too much about the details of how they shared this bell pair. But the key point is that this process, sharing a bell pair, is not necessarily secure. Okay, so we'll assume that there's some possibility that somebody could have eavesdropped on this process or measured the state some point earlier, or changed the states that actually it's not the bell pair they thought it was. They can't be completely confident in advance that this thing is a bell pair, but eventually they're going to be able to do some tests to prove that it really is. Okay. And now both of them are going to measure in either the X or the Z basis. It's important that they don't tell each other which basis they're going to use in advance. They just choose them independently, but then throw away qubits where they measured in different bases. This is exactly like BB84. Okay, if they told each other in advance what bases they were going to measure in, then you might worry that somebody could take advantage of that. Okay, so they've now, in all the qubits all the bell pairs that we've keeping, they've either both measured in the Z basis, i.e. the 0, 1 basis, or they've both measured in the X basis, i.e. the plus minus basis. Right? Pretty easy to check. I leave it to you guys in exercise that if I use a measurement operator that's just tensor product of Z on qubit 1 and Z on qubit 2, and apply it to the bell state, phi plus, it just gives phi plus. Each of the Zs give a -1 to the 1, 1 term, -1 phase to the 1, 1 term, but those just multiply to 1, so you have the same state. So that means the product of the two measurement outcomes is always equal to 1. This measurement operator that's just the tensor product of the two measurement operators is, its measurement outcomes are the products of the Alice and Bob's two individual measurement outcomes. In other words, the two measurement outcomes are the same. If Alice gets 1, then Bob gets 1. If Alice gets -1, then Bob gets -1, so that they multiply together to give 1. This is guaranteed 100% of the time. Alternatively, they both measure in the X basis. In that case, we look at the measurement operator X on qubit 1, tensor X on qubit 2. So again, just looking at phi plus written out explicitly, X tensor X acting on 0, 0 takes it to 1, 1. X tensor X acting on 1, 1 takes it to 0, 0. So again, this takes phi plus to phi plus. Again, two measurement outcomes always agree.
Sorry, could you explain again why C1 cross C2 of phi plus is phi plus?
Yep. No, that's a good question. Let me explain that properly. Okay, so if I have a measurement O1, or I'll call it measurement OA, done by Alice. Let me call these A and B actually. A, B. Right, we can write that as a sum over all measurement outcomes for Alice's measurement times the measurement outcome, MA, times the projector for that measurement outcome, right? The projector onto the eigenspace. Similarly, OB, sum over MB, MB projector onto the eigenspace associated with MB. OA tensor OB of MA and B times projector onto MA tensored with projector onto MB. Okay, this product of the two projectors gives you the probability of getting the measurement outcome. The product of the two probability of getting the product of the two projectors is the probability of Alice getting outcome MA and Bob getting outcome MB. Okay, so we just look at this measurement here. This product of the two measurement operators, that's telling you that for each case where in the original measurements we would have got MA for Alice's measurement and MB for Bob's measurement, then in this product measurement operator we get the outcome MA times MB. Okay, this just comes from tensor producting the two operators together and using linearity to take these things out the front. So that means the fact that this operator phi plus is an eigenstate of X tensor X means it is in if I add up all the projectors where MA times MB equals 1, then the state phi plus is preserved by the sum of those projectors. I.e. with 100% probability, I will get some outcome for MA and some outcome for MB such that they multiply together to give 1. Does that answer your question?
Yeah, thank you.
Great. Okay, so this is just a useful trick that I probably should have explained better originally, for how you can work out like what the product of the two outcomes is just by looking at one measurement operator. Okay. So whichever basis they measure in, then Alice and Bob get the same answer, and they just use their answers as the secret key. Okay. What can Eve do? To try and interfere with this? Well, she can interfere with the process whereby they're sharing this Bell state, so that it's not actually in the Bell state, or maybe it's even entangled with some state that she has, right? Change state. So it's not phi plus, e.g. it's entangled with her stuff. That's pretty much the only way she can interfere with the non-secure preparation of the entangled state. But it's pretty easy to check. It's just some linear algebra. the only state psi such that ZA tends to ZB psi equals psi, i.e. if you measure in the Z basis, you'll always get the same outcome for both Alice and Bob, and XA tends to XB psi equals psi is actually phi plus. So anything else she does to that state, or any way she entangles it, so it's like phi plus times some state that she has plus some different state to phi plus times something else, then it will always be the case that Alice and Bob won't always get measurements that agree. Okay? Anything Eve does will make Alice and Bob's measurements disagree.
I'm sorry, I think I just missed one comment. When you say that Eve can change the state so it's phi plus, what did you mean there?
I meant that. Right, so while the state is being shared, she could like measure it, which would change the state. She could apply some unitary operator. She could do some like thing that unitary that acts on her qubits as well and entangles with her qubits. There's a lot of stuff she could do. But you know, to have an effect, then she needs to change the state of Alice and Bob's Bell pair so that it's not phi plus, or at least, yeah, it's not phi plus tensor, whatever she has. Okay.
Makes sense.
Thanks
Thank
for
you.
the question. So anything Eve does will make it so that their measurements don't always agree. That means, as with BB84, by testing some random, checking some random fraction of the secret keys, Alice and Bob can detect Eve's influence.
I have a question about this actually. Yep. I might have missed this. I was busy for 1 second, but what's the proof, or how do we know that there's no other state for which these two operators in particular act as the identity?
I didn't prove it to you, but you can just check. So these two operators commute with one another. So individually, X and Z anti-commute. So X times Z equals minus Z times X. But when you take the product of two of them, that means they commute. Okay. And so that means they have a shared eigenbasis. Okay. The eigenvalues of Z tends to Z are plus and minus 1. Each subspace is 2-dimensional, right? The full Hilbert space is 4-dimensional. So each of them has, there's a 2-dimensional subspace in each case satisfying these equations. And you can just see what those are. For the Z's, it's spanned by phi plus and phi minus. For the X, it's spanned by phi plus and psi plus. Let me check that's right.
I think the simultaneous eigenbasis of these operators is indeed the Bell basis.
Yeah, exactly. Yeah, that's so you can just check the 4 Bell states, and the only one that has eigenvalue 1 for both Z tends to Z and X tends to X is phi plus. Okay. So it's just some pretty trivial linear algebra on 4-dimensional, 4-dimensional Hilbert spaces.
Another question.
Yep.
For our measurement basis, do we have to choose X and Z, or can we just choose any basis such that our new state will still be in a Bell state? Because then their measurements.
So, yeah, this is a good question. It is helpful having these things commute with one another because it just makes it easy to argue that this is the simplest pair to choose, I think, because they commute, and so you can say this is really the only eigenstate where it's +1 for both. I think you could use a measurement on the Bloch sphere at some any measurement in the Bloch sphere with phi equal to either 0 or pi tensored with itself will be an eigenstate of phi plus with eigenvalue 1. That's a fact. I think what will be the case is as long as the angle on the Bloch sphere between your two measurement bases isn't too small, then it will work. I leave that to you as an exercise to check that that's true, but it will be slightly more annoying to prove because they won't commute anymore. But yeah, I'm pretty sure you can make the argument with plenty of other operators. Okay. It's worth noting that as with BB84, this is vulnerable to man-in-the-middle attacks, right? If when Alice and Bob are thinking that they're checking that they have the same secret keys for some random sample, then actually they're not talking to each other, they're talking to Eve, then they have no security at all. So they need to have some way of verifying when they do the comparison of their keys that they're actually talking to each other. Other comment is that actually the easiest way to prove BB84 is secure is just to think about it as a special case of Ekert 91. What do I mean by that? Well, let's say that Alice actually did her measurement on the Bell pair a bit earlier, okay? And she just kept it secret, didn't tell anyone what basis she measured in. That shouldn't affect anything. It doesn't matter what time she did the measurement. But now, if she measures in the Z basis, then really instead of sending half of a Bell pair to Bob, she's actually sending either the 0 state or the 1 state randomly chosen, right? Once we post-select, once we project the Bell state into either 0 or 1 on Alice's qubit, then Bob's qubit also gets projected to either 0 or 1. Similarly, if she does the measurement in the X basis, then she's really sending either the qubit plus or the qubit instead minus to Bob. This is exactly BB84. So BB84 equals Ekert 91, but with Alice doing her measurement. Alice measuring her qubit before sending the other half to Bob. Great. Okay, so that is all I'm going to say about QKD. I promise it's finally not going to show it up anymore. It might appear on homework 3. I'm not completely sure about that. Haven't decided yet, but certainly not going to talk about it anymore in lectures. So now I'm going to move on to a new topic, which is unitary circuits. This is for the first time we're meaningfully going to be starting talking about quantum computers. Okay. So back last Thursday, I think it was, we talked a decent amount about, dynamics of quantum systems and how, that there's some unitary dynamics that you can split into infinitesimal pieces, and it's called the Schrödinger equation for some Hamiltonian H. But in that context, and sort of normally when we do quantum mechanics, we assume that the Hamiltonian H in Schrödinger's equation, or sort of equivalently U, T2 to T1, the sort of time evolution operator, is sort of given by the laws of nature, right? That's some input that we don't get to control. We just deal with it, and we like learn what it is because we're clever physicists for some particular system, and then we use that to make predictions. The central feature of what it means to do quantum computing is that we basically have we assume we have such control over the system and the environment it's in that we can basically make the Hamiltonian be anything we want. So we have so much control. Sorry, not doing well, I'm writing here. That we can say we can apply any unitary gate. So again, quantum computing language just means any unitary operator acting on some qubits that we choose to. Okay, that's what it means to have a programmable quantum computer. Just like for a programmable classical computer, we can apply like an AND gate to 2 classical bits, or a NAND, or a OR, or any particular basic building block that we want. In quantum computing, we assume that there's some basic set of sort of unitaries, and we'll talk later about what it means to have sort of enough unitaries that you have sort of a universal computer, like a universal classical computer can be built out of NAND gates. That we can just dial the Hamiltonian to be whatever we want by changing the environment the qubits are in, so that we can make them evolve in time using any particular unitary matrix. There's a big but here, which is that if I have some large computer, so say the Google quantum computer is at 50 qubits, we imagine in 20, 30 years, we might be dealing with millions of qubits, then we're not going to be able to just apply some arbitrary matrix to the million qubits all at once, right? You have some 2 to the million dimensional Hilbert space describing that qubit. And if I gave you a 2 to the million times 2 to the million unitary matrix, I'm not going to be just able to say, oh, do that, my quantum computer. Like, go, obey me. I'm going to turn on this random Hamiltonian that does it. So instead, we're only going to be allowed to interact a small number of qubits at a time. Maybe 2 or 3 or whatever. So this is just like a classical computer, right? In a classical computer, you can apply an AND gate to 2 qubits. You can do whatever to 2 classical bits. You can do whatever you want to 2 classical bits very easily in like a small number of elementary steps. But if I have some very complicated classical function that I want to apply to a million megabits worth of data, then it's going to take me a load of time, and I'm going to need to break it down into smaller building blocks that I can actually do. Okay, so this is just like that. So if I have some state psi on this Google quantum computer with 54 qubits or whatever it has, then my sort of computer program will be to take that state psi, and then maybe I apply some unitary that interacts qubits 1 and 2. Okay? And then maybe I apply some unitary that interacts qubits 2 and 8. Then maybe, I don't know, 7 and 1. Then maybe 29 and 7. So these labels are just meaning that this unitary only acts on sort of the 4x4 Hilbert space, the 4-dimensional Hilbert space that is the tensor product of those two qubits, and so on. We call this a unitary circuit. This model of quantum computing, where a quantum computer is treated as a system where you have some quantum state and then you apply unitaries interacting a small number of qubits at a time, is called, sensibly enough, circuit model. We're going to see that there's other models of what it means to have a quantum computer that end up being pretty equivalent, but this is sort of the most standard one. So one thing you might notice about this sort of circuit I've drawn here is that it's pretty hard to keep track of what's going on. This is generally true, right? This was really a very simple thing, like only, 1, 2, 3, 4, 5 of the qubits have had anything done to them at this point. So that means 49 of the qubits have just been left completely untouched. In a practical circuit, you're going to be interacting all of the qubits together. Going to be all sorts of stuff going on. We're going to need, if we're going to try to understand these sort of algorithms, much better notation for visualizing these things and understanding what they mean. So as I say, if you take anything away from this lecture, the thing I want you to take away is understanding what this notation is. It's called circuit diagrams. So as I say, it was not originally invented for quantum computing. It was originally invented by Roger Penrose for doing GR stuff, I think. Basically the same notation was. So yeah, please, if anything's unclear in this, please ask questions, because this is really important to get comfortable with. You should be always asking questions, but particularly now. Okay, in this notation, qubits are written as lines. Okay, so if I have, say, 3 lines here, that equals the tensor product 3 qubits. Should note, sometimes one line can mean a larger Hilbert space than just a qubit. Can be a qubit, as it's sometimes called, for some arbitrary dimension d. So you could have 3 qubits just all represented in one line. But if you want to treat all your qubits separately and then interact them, then each qubit should get a separate line. Okay? Now we need to represent unitary matrices being applied to these qubits some way. unitaries, we're just going to represent as boxes. And they're going to be boxes that have input lines coming in from the left and output lines going out to the right. And those lines are the qubits that unitary does stuff to, right? So really, you know, if I have sort of a system like this, so I have 4 qubits, and then I have 2 of them go into this box, and the other 2 just go straight through. That describes the circuit that just looks like some unitary acting on the first 2 qubits, tensored with the identity acting on qubits 3 and 4. Right, we'll often drop the fact that it's tensored with the identity and just right that it's equal to just a unitary acting on 1 and 2 and nothing happening to qubits 3 and 4. And in circuit diagrams, we conventionally have time going from left to right. So people sometimes do things differently. So this is, you know, this circuit, the input is on the left, the output is on the right. Note that this is sort of the opposite of matrix notation, where in this circuit up here, the first thing that got applied was this unitary U12, and then the unitary U28, and so on. So it goes right to left in that case. It's kind of confusing that they're different, but honestly, that's, well, left to right makes sense for a circuit diagram, I think. I wouldn't want it to be the other way around. It would be very confusing. So just to give a sort of more general example, we could imagine some system consisting of, I don't know, let's make it like 8 qubits. Okay. And then we could imagine that our quantum computer interacts the first 2 qubits, applies a unitary U1 to it, and then maybe it interacts qubits 2 and 3, applies some different unitary U2 to them. Note that the 1 and the 2 here just represent the fact that these are different unitaries. I'm no longer needing to label which qubits the unitaries are acting on because that's done by my notation, right? It's clear from the circuit diagram that this one is acting on qubits 2 and 3. Then maybe I could apply some unitary U3 to these qubits. And again, very nicely, you know, because this unitary U3 acts on completely different qubits to U1 and 2, i.e. it commutes with them, then there's no reason I had to draw that to the right of U2 because it doesn't matter whether it was applied before or after U2, because the two operations commute. Could, in principle, you probably wouldn't do this in a quantum computer, have some bigger unitary that acts on sort of all of these at once, does something more complicated to them maybe. Call that U4. Maybe we do a bit more to these 2 qubits. 5. And let's just let the rest go through unchanged.
In this notation, how would you show something acting on like bits 1 and 8? Is that difficult?
Yeah, so I could, good question. It's a bit more notationally messy. The easiest thing to do, if you have a simple enough circuit where you can do this, is to just move qubit 8 up to be in the second position, right? But you know, I can just draw lines crossing over each other, so I could have a line starting down here, and then it comes up here and interacts U6 like this, right? So you know, the topology of the network can become complicated, but in principle, the notation can deal with anything.
Right.
Cool. Okay. Great. So that is an introduction to some notation. Really, for the rest of this lecture, we're just going to do what I call a spotter's guide to important unitary gates. So we're just going to go through a load of unitary gates that you're going to see in future lectures. Won't be the most interesting thing in the world, but you know, it's going to be important for that next lecture. We're going to start seeing some really cool stuff done with unitary circuits. In fact, next lecture, we're going to see quantum teleportation, which is always fun. Okay, so let's start with the simplest unitary gates you might come across, which are just gates acting on one qubit. Can anyone think of some important examples of unitary gates, the unitary matrices that act on one qubit? Someone say something.
The identity.
The identity. Okay, that's too boring. I'm not going to write down the idea.
Flip gate.
Identity. Great. Say that again.
Flip gate.
Flip gate. Awesome. So in other words, a gate that takes 0 to 1 and 1 to 0. Anyone know what that gate is called? We've seen it before in a different, very different.
Poly X gate.
Awesome. So the unitary matrix that describes a flip is just the Pauli X matrix, right? Take X 0 equals 1, X 1 equals 0. This is the Pauli X matrix, and indeed it acts as a bit flip. There's a very important point here that I really want to emphasize because it's really key to not getting very, very confused. Okay, previously we were talking about Pauli gates at Pauli matrices as measurement operators. Okay, now we're talking about Pauli matrices as unitary gates. This is a weird thing about the Pauli matrices, that they happen to be both Hermitian and unitary as unitary gates versus measurement operators. Yeah, so all the Pauli matrices happen to have x squared equal the identity and x equals x dagger. So that means that they're Hermitian, but they're also unitary, okay? And Hermitian operators and unitary operators in quantum mechanics play two very different roles. Hermitian operators we use as measurement operators. Unitary operators get used as unitary gates. Okay, these are completely, the same matrix as a measurement operator does a completely different thing to the state versus using that matrix as a unitary gate, right? So if I apply x as a unitary gate to some state, to say the state 0, then it will become, my final state will be the state 1, right? The final state will literally be unitary matrix applied to initial state. This is our postulate 3 of quantum mechanics. If I apply a measurement with measurement operator x to a state in state 0, the final state will not be 1, it will still be 0, and I will get a measurement outcome that will be, ignore what I just said. If I measure using the x operator, then I will get the plus state with 50% probability and a measurement outcome of 1. And with 50% probability, I will get the minus state and a measurement outcome of -1. Okay, if I apply it as a unitary gate, I will just get the state 1 and I will not have a measurement outcome because I did not do a measurement. Okay, hopefully that is clear to people, but it's really important to not get confused between those two roles. It's sort of unfortunate that the simplest matrices in both cases are the same matrices, even though in general, the class of matrices that show up, unitaries versus summation, are totally different.
How does the system know that the X matrix is being used as a unitary gate versus a measurement operator?
Yeah, so this is one of those things where it's a lot more obvious to the system than it is to you. So, yeah, to apply this thing as a unitary gate, what will I do in practice? I'm gonna like dial the environment the unitary is in to turn on a Hamiltonian for the right period of time in order to have the time evolution be given by this matrix X. Okay? To do a measurement in the X basis, then, for example, for my qubit is a photon, then I'll just measure the polarization in the horizontal basis. Sorry, the 45 degree up, right, left, down, but linear polarization basis. I'll stick a polarizing filter at 45 degrees and see whether the qubit gets through or not. Yeah, so yeah, the what you do physically depends on the system. But if you want to apply this thing as a measurement operator, then you're going to measure the system. However, you can do that in practice. Like, yeah, you have some photon detector, you have some, you do something that lets you measure it. I don't know, I'm not an experimentalist. If you want to apply it as a unitary gate, then you need to control the energies of the different states of the qubit to control the Hamiltonian for some amount of time to give you some particular time evolution. But there's no way that the set of things you do will just be totally different for any given qubit. Okay, it's really just us that are likely to get confused because we're seeing the same mathematical matrix showing up. Okay. Another matrix, unitary matrix that you could apply pretty obviously is the Z matrix. This takes 0 to 0, takes 1 to -1. Of course, as we all know, -1 as a quantum state is really the same state as 1. So this matrix hasn't done anything to 0, hasn't done anything to 1, so it doesn't actually do anything to the quantum state. So this Pauli Z, which seems like it's a non-trivial matrix, but it doesn't actually do anything to quantum states. Everyone agree with that? Anyone disagree?
Not if you're in a superposition.
Indeed. Okay. That is, of course, complete nonsense, everything I just said. If I apply Z gate to the plus state, right, so 0 plus 1, then 0 goes to 0, but 1 goes to -1. So we end up in a minus state. Similarly, Z on the minus state is equal to the plus state. So Z is doing just as non-trivial stuff as X. It's just doing so in a different basis. So this phase matters for superpositions, and also if it's sort of entangled with another system or something like that. But yeah, even though it doesn't do anything to the 0 state and the 1 state, that doesn't mean it doesn't do anything to superpositions. So this state, this operator is called, sensibly enough, a phase flip. Okay, anyone got other examples of 1 qubit gate that you might apply?
Sigma Y.
Yeah, so there's one more Pauli matrix, which is the Y matrix. We don't often talk about this as sort of a fundamental unitary gate. Anyone know why? Anyone care to guess why?
You can just get it from X and Z.
Exactly. So Y is equal to, I can't be bothered to remember the sign, but it's either IXZ or it's minus IXZ. So I can apply Y by just applying Z and then applying X. And then if I wanted, applying a global phase, but that doesn't really mean anything because, you know, global phase doesn't change the state. So basically to apply Y, then I just apply Z and apply X, or the other way around. So I guess this is bit flip combined with a phase flip. But in general, when we talk about unitary gates, we just talk about X and Z. Note that this is a big difference from measurement operators, right? Doing a measurement operator in the Y basis is very different from doing a measurement in the X basis and then doing a measurement in the Z basis. Okay. Again, these are just, you know, the same matrices showing up just because there aren't many 2x2 matrices, but yeah, fundamentally playing pretty different roles. So there's one particular property of all of these Pauli matrices, which is pretty non-typical actually, which is any of these matrices preserve the 0, 1 basis, right? If I start with some state in the computational basis, say 0, and then apply X gates to it and Z gates to it and stuff like that, I'll always end up with either 0 or 1, right? So, you know, this is pretty boring, right? Normally with a quantum circuit, or quantum computer will imagine that the state is initialized with just everything in zeros, just like when you turn on a computer for the first time, probably going to have everything be 0 that's not being used. And if we're only able to take 0 to 1, then we're always going to have a state in computational basis. We're never going to have superpositions. We're never going to take advantage of the power of quantum mechanics, right? So we need some other gates that don't preserve these things. Does anyone know the most famous example of a matrix that does not preserve the 0, 1 basis that will show up all the time?
Gate.
Awesome. It's called H. The Hadamard matrix or the Hadamard gate. And this is defined by H acting on 0 being equal to the plus state, and H acting on 1 being equal to the minus state. Okay, so this switches the computational basis, the Z basis, with the plus or minus basis, i.e. the X basis. Some comments about the Hadamard state. H is actually equal to H dagger. It's its own inverse. Like with the Pauli matrices. So if we apply it twice, we get the identity. Okay. So yeah, that just makes sense, right? If we switch the X basis with the Z basis and then we switch them again, we're back in the original basis. And generally, yeah, the Hadamard matrix is going to be a super useful, probably one of the most important gates that you're going to see show up time and time again. So that's a bit better. That's now we have the Hadamard, we can start creating like superpositions and stuff. At least we can get somewhere. It's still pretty limited, to be honest, but it's a lot better than we had before. But even if we have sort of arbitrary 1 qubit gates, there's a lot more, this is still just a very limited set of 1 qubit gates. You could have much more complicated ones. Even if you have any 1 qubit gates, then we're still missing out on some big aspects of quantum mechanics. Namely, if I start in some state, psi, tensor, phi, and then I apply 1 qubit gates to each of them. This goes to U1 psi, goes to U2 psi, it's still a product state. So just using 1 qubit gates, we have no way to create entanglement between different qubits. Again, entanglement is pretty important to a lot of quantum computing. So we're going to want, we need stuff better than that. In particular, we're going to need 2 qubit gates. And in fact, with any two qubit gates, then by combining them together, combining enough 2 qubit gates together, then we can approximate any unitary on arbitrarily many qubits. I want to emphasize at this point, I'm only claiming that this is true if you can apply any 2 qubit unitary matrix to any pair of qubits. We'll later in the course, we're going to see some weaker conditions that will let you do the same thing. Okay. So let's see some important examples of 2 qubit gates. So the most important 2 qubit gate that you will see in all of quantum computing is what's called the C0 gate. C0 here meaning conditional not.
Sorry, quick question.
Yep.
So is the claim that using only 2 qubit gates, we can approximate any unitary to arbitrary precision? Like we can get as close as we want?
Yep.
Cool.
Okay. So this gate is so important, in fact, that it gets its own notation. It's not just written with a box acting on the 2 qubits. Different places use different notation. I'm going to stick with the textbook's notation, although it's maybe not the most standard one, which looks like following. We have a dot on one of the qubits. This is going to be called the control qubit. Then we have a cross on the other qubits line, and these 2 qubits are connected together with a vertical line. This does not mean there's a qubit going from one to the other. It's just a different notation. Only horizontal lines represent qubits. And this second qubit with the cross is going to be what's called the target qubit. So what does this C0 gate do? Well, it's very simple. If the control qubit is in the 0 state, then it does nothing to the target qubit. It just leaves the target qubit unchanged, applies the identity operator. But if the control qubit is in the 1 state, then it flips the target qubit. So it applies an X gate, applies a NOT to the target qubit. In other words, C NOT of 0, 0. First qubit is in state 0, so it does nothing to the target qubit. State 0, 0. C NOT 0, 1. Again, does nothing to the target qubit, so it stays 0, 1. C NOT of 1, 0. Control qubits in state 1, so that means we apply a NOT gate, an X gate to the target qubit. So this gives 1, 1. Similarly, C NOT of 1, 1 gives 1, 0. In other words, in the computational basis, C NOT is the matrix 1, 1, 1, 1. Add a load of zeros. Whoops. Try not to add too many zeros, but add a load in. Again, as with a lot of these states, C naught squared is the identity, it's its own inverse summation. But yeah, this control NOT gate is going to be super important. In particular, if I start with, whoops, apply C naught to say plus tensor 0. So I start with a product state. This is 0, 0, which goes to 0, 0. Plus 1, 0, which goes to 1, 1. So C naught, even though it seems like a sort of very classical gate that just takes the computational basis, when it's applied to input superposition, then it can be used to create entanglement. It can be used to create Bell states. Okay? So that's a very useful thing that it can do. In fact, this idea of a control qubit and a target qubit is so useful that we also have special notation for what's called just a general controlled U gate for some arbitrary unitary matrix U. So again, just have a dot, but now you're going to have a U in a box. Okay, and this, anyone guess, based on the control NOT gate, what this controlled unitary gate will mean, what this does to the two qubits? So control NOT had, if the first qubit was in 0, it just did the identity. If the first qubit was in state 1, it applied the X matrix, a NOT gate. What do you think this controlled unitary might do?
Apply the unitary only if, depending on the state of the control qubit.
Awesome. Thanks very much for somebody answering. I know there's a lot more people who know. I also know that it's like easy to be shy and quiet on Zoom, but it's helpful for me if someone answers. So a controlled unitary gate, which I'll call maybe CU. just does nothing if control qubit is in state 0. If the control qubit is in state 1, it applies the unitary. Okay? These things are going to be super useful, going to show up all the time. There is a very important point to be careful about here, which is that naively, classical intuition seems to tell us that nothing is happening here to the control qubit. Right? Seems like, you know, the control qubit just decides whether something happens to the target qubit, but doesn't actually have anything happen to itself. This is not true. Quantum mechanically, just as much is happening to the control qubit as is happening to the target qubit. It's just the basis where stuff's happening is not the computational basis. Okay. To see this, let's consider the following pretty simple circuit. Going to have 2 qubits. Going to apply a Hadamard to each of those 2 qubits. We're then going to apply a C0. Top one is the control qubit. And we're then going to apply Hadamard gates. Okay? So remember that the Hadamard squared just flips the X and Z basis twice, so it's just the identity. So this top qubit has a Hadamard applied, then it just controls something else, but nothing happens to it, and then applies another Hadamard. So seemingly, nothing happens to the top qubit. We'll see that this is very definitely not the case. Okay, let's just consider all the possible inputs here. I'm just going to do this very explicitly because it's good practice for the later stuff. Say you start with the input being in the 0-0 state. Okay, now let's imagine we apply Hadamards to each of the 2 qubits. What's the state going to be? Someone tell me here. I don't want to be saying any of those things, and we've got a lot of steps to go through, so people need to chime in fast.
Plus plus.
Awesome. Apply 2 Hadamards, it goes to plus plus. What about when we apply a C0 gate to plus plus? This one's a bit more non-trivial, but if we go up to what the C0 does, plus plus looks like 0-0 plus 0-1 plus 1-0 plus 1-1. Okay, so that's going to go to 0-0 plus 0-1 plus 1-1 plus 1-0, which changed the order of the terms in the sum, but it left it unchanged. So that stays as plus plus. And then apply 2 Hadamards to plus plus. What happens to it? Come on, someone.
Get back to 0-0.
Right, great. Hadamard switches the X and Z bases, so plus plus goes back to 0-0. So 0-0 stays as 0-0. What about 0-1? Apply 2 Hadamards, what do I get?
Plus minus.
Awesome, plus minus. Right, 0 goes plus, 1 goes to minus. So this is now plus minus. Let's just write it out explicitly. Plus 1-0 minus 0-1 minus 1-1. So what does this go to when I apply the C0?
Sorry, is the first qubit like the top one, and then the second one is like
First
the bottom?
qubit is the top one, second one is the bottom one, yep. Okay, so let's just write this out very explicitly. 0, 0 goes to when I apply C naught. Come on, guys.
0, 0.
Yep, 0, 0 stays 0, 0 because the first qubit is in state 0. What about 1, 0?
1, 1.
Right, great. So the first qubit's in state 1, so it gets flipped, so it goes to 1, 1. What about 0, 1?
State 0, 1.
Stays 0, 1 because first qubit is 0. What about 1, 1?
1, 0.
Goes to 1, 0. Awesome. What is this state? Anyone know? Has a,
Minus.
yeah, indeed. We have a minus sign in front of both 0, 1 and 1, 0. Okay. So this is actually exactly the same thing as minus, minus, right? The two minus signs cancel out in some 1, 1 term, and that's why you get a plus. Okay, final step, we apply two Hadamard's. What does minus, minus go to? Come on, someone.
1, 1.
1, 1, indeed. Switch the two bases. So our starting state of 0, 1 has ended up in 1, 1. The control qubit for the C naught has got flipped. Let's check the other two cases just to see the rest of what happens. 1, 0 goes to, when I apply two Hadamard's. Come on, guys.
Minus plus.
Minus plus. Minus plus is a half. 0, 0. Minus 1, 0. Plus 0, 1. Minus 1, 1. That goes to half. 0, 0. Minus 1, 1. Plus 0, 1. Minus 1, 0. It's just exactly the same thing. It's minus plus. And then I had them on minus plus. What do I get?
1, 0.
1, 0, indeed. So 1, 0 stays as 1, 0. Final case, 1, 1 goes to. Come on, guys. Keep shouting out.
Minus, minus.
Minus, minus. So minus, minus is a half. 0, 0. Minus 1, 0. Minus 0, 1. Plus 1, 1. This goes to a half. 0, 0 stays the same. 1, 0 goes to 1, 1. 0, 1 goes to 0, 1. 1, 1 goes to 1, 0. Second qubit gets knotted. So this one is plus minus. Plus minus goes to, come on, guys.
0, 1.
0, 1. Indeed. So this whole circuit takes 0, 0 to 0, 0. 0, 1 to 1, 1. 1, 0 to 1, 0. And 1, 1 to 0, 1. There's a name for that circuit. What is it? It's a very simple circuit. You can do it in one step.
The control not with one being the control qubit.
Exactly. This is just a control NOT gate, but now the control qubit is on the bottom and the target qubit is on the top. Okay? So by applying all these Hadamards, we switched around what the control qubit is and what the target qubit is. Okay, so that was very explicit and boring going through the steps. I'm now going to show you a sort of simpler way to see this in the last few minutes. I know this isn't the most exciting thing in the world, but it's just trying to give you guys a sense of how to play around with these circuits, because we're really going to start doing interesting stuff with them next time. That's to instead think about a controlled Z gate. Okay, so what does this do? Take 0, 0 to 0, 0, obviously. 0, 1 to 0, 1. So the control qubit's in state 0. Then nothing happens. 1, 0. It applies the Z gate, but the Z gate doesn't do anything to 0, so that stays as 1, 0. Finally, 1, 1 goes to minus 1, 1. Anyone notice anything about this? Well, I'll just say it. This is exactly the same operator as a controlled Z gate, where the control qubit is the bottom and the target qubit is the top. Okay. Also going to need another couple of useful results. Just the following two little mini circuits. The first is HZH. Okay, so what does H do? Switches the X basis and the Z basis. Okay, so that means the X basis coming in here gets switched to Z basis, has a Z applied to it, then gets switched back to the X basis. That's exactly the same thing as just applying an X gate. Similarly, H, X, H is the same thing as applying a Z gate. Okay. Now let's start with our simple C0 circuit here that has the control qubit on the bottom, target qubit on the top. We can rewrite this controlled NOT as a controlled Z with Hadamards either side of the Z. Why does this work? It's because the control gate either applies the identity gate or it applies the Z gate. If I sandwich the identity gate with two Hadamards, I just get the identity because the Hadamard is its own inverse. If I apply the Z gate and sandwich it with H gates, then I get an X gate, so I get a control NOT. Okay, but now can use this equality we had before, where it doesn't matter which qubit is control and which is Z, to make it so that I call it a controlled Z, where the control qubit is now the top one. Finally, I use exactly the same trick to say that a controlled Z is the same thing as a controlled X, i.e. a C0, with a Hadamard either side. Okay, so I've just proved exactly the same equality that I proved before, but I've done it without using any explicitly writing out matrix elements that say what happens to them all, which in practice gets pretty horrendous for all but the simplest circuits. Instead, I've just used sort of some different matrix identities in order to rewrite the circuit in sort of simple steps and eventually end up sharing an equality between the two. Okay, so yeah, as I say, today's wasn't the most exciting lecture, but on Tuesday, I think it should be a lot more exciting. We're doing quantum teleportation, and also an equally cool, though less sci-fi named thing called superdense coding. There'll be our first, if you like, practical quantum circuits that let you do interesting things. Yeah, I'm going to stop the recording. Homework 2 is due tomorrow at 6 p.m. Feel free to ask me questions afterwards, but for now, I'm going to stop the recording.